Hola, buenas tardes. Bienvenidos al webinar de hoy a todos los asistentes. Voy a comenzar presentando a los ponentes que tenemos hoy con nosotros. Por un lado tenemos a David Torres, Wind Energy Manager de TÜV SÜD. Buenas tardes, David.
Hola, buenas tardes.
Buenas tardes. Bueno, David es todo un experto en el sector, lleva en la eólica desde 2007. Ha trabajado principalmente en consultoría y asesoría técnica en todas las fases prácticamente de desarrollo de los proyectos, en recurso eólico, ingeniería, construcción, operación y mantenimiento. Y lleva desde 2018 en TÜV SÜD como Wind Energy Manager para España y Portugal. Y por otro lado tenemos a Henry Ávila, es Senior Project Manager en TÜV SÜD. Hello Henry, good afternoon, welcome.
Hola, buenas tardes.
Buenas tardes. Henry también lleva muchísimos años en el sector, desde 2005, y ha trabajado tanto para diversos fabricantes y suministradores como para operadores y promotores de parques eólicos, también en diferentes fases. Lleva en TÜV SÜD desde 2014 y bueno, va a ser quienes nos van a ilustrar hoy sobre el tema de la detección y anomalías en el funcionamiento de los aerogeneradores. Como breve introducción, antes de daros la palabra, bueno, comentar que en España, casi todos lo sabréis, pero tenemos ya una flota de aerogeneradores muy importante instalada, alrededor de 21.000 aerogeneradores, representan algo más de 26 gigavatios de potencia y de los cuales más de la mitad ha superado ya los 15 años de operación, es decir, tenemos una flota relativamente antigua por haber sido uno de los primeros países en Europa y en el mundo de arrancar con la energía eólica. Además, pues no solo estos parques quizás un poco más antiguos, sino también los parques nuevos, los nuevos desarrollos, pues están expuestos a una elevada presión en costes cada vez mayor, cada vez existe más competitividad en el sector, la introducción de estas últimas subastas renovables con precios adjudicados muy bajos, notablemente inferiores a los precios de mercado actuales en el pool. Pues todo esto está forzando cada vez más a una competitividad y a una necesidad de optimizar cada vez más la operación y el mantenimiento de los parques. Es un tema clave para el sector desde siempre, pero si cabe, pues todavía aún más. Y entre los principales objetivos de las empresas, pues obviamente está maximizar la producción, la disponibilidad del parque, evaluar correctamente todas las cargas y la fatiga de operación que va experimentando el parque durante su vida útil para poderla luego extender lo mejor posible. Y por eso es clave el tema de hoy, la identificación de los problemas de operación, el poderlos cuantificar, el medirlos y poderlos corregir a la mayor brevedad. Hoy en día, todos los sensores que llevan equipados los aerogeneradores y los sistemas SCADA, pues nos proporcionan una gran variedad de datos, muchísima información, pero esto no es condición suficiente para identificar bien los problemas, ¿no? El diagnóstico a partir de ellos tampoco es tarea sencilla si no se dispone de un buen análisis estructurado que permita llegar a conclusiones válidas de dónde pueden estar los problemas de operación o los puntos de mejora, ¿no?, para optimizarlos. Por eso, pues el webinar de hoy es muy oportuno. En TÜV SÜD nos van a exponer cómo con una metodología adecuada de análisis es posible analizar bien toda esta información procedente de los SCADAs, identificar problemas concretos de operación y optimizar la gestión de los parques. Por mi parte, nada más. Te dejo la palabra, te cedo la palabra, David, y cuando quieras, pues podéis proceder con vuestra presentación.
Pues muchísimas gracias, Tomás, y como siempre agradeceros también la gran organización de estos webinars y habernos dado la oportunidad de hacer esta muestra hoy, ¿no? Entonces, bueno, yo en el día de hoy simplemente voy a hacer un nexo introductorio hacia mi compañero, ¿no?, para contaros un poco de qué vamos a hablar hoy, para que luego la parte más técnica específica sea comandada por mi compañero, como os digo. Simplemente unos segundos para los que no conozcáis la compañía como tal. Bueno, pues somos TÜV SÜD, somos una compañía de origen alemán con más de 25.000 empleados y oficinas en todo el mundo. Y bueno, aparte del sector energético, pues también nos dedicamos a otro tipo de industrias o sectores como puede ser el médico, infraestructuras, sector químico, movilidad, ¿no? Y específicamente en el tema eólica, bueno, pues somos normalmente más conocidos, sobre todo aquí en el sector español, en el tema de certificación de turbina o de emplazamiento, pero de igual modo, bueno, pues hacemos una asistencia técnica a nuestros clientes durante toda la fase de desarrollo de un proyecto, pues en servicios comunes como puede ser el tema de recurso eólico, desarrollo de ingeniería, operación y mantenimiento y temas de rendimiento como va a ser el tema que vamos a tratar hoy. Bueno, por introducir un poco y empezar, aquí vemos una situación que desde un punto de vista del operador, bueno, pues sería una situación ideal, ¿no? Nuestra turbina está trabajando en muy buenas condiciones, está adaptando perfectamente a nuestra curva contractual de potencia, pero ¿qué sucede cuando nos encontramos algo así, ¿no? Bueno, pues normalmente nuestros clientes o el operador del parque va a tener unos departamentos específicos para el análisis de los datos de SCADA o, en nuestro caso, bueno, pues tira de empresas externas, como puede ser nuestro caso, para averiguar un poco qué es lo que está pasando. Entonces, la pregunta es, ¿cuál es el problema aquí, ¿no? ¿Cuál es el problema? Bueno, pues esta respuesta, como muy bien introducía Tomás, no es una respuesta sencilla, sino que hay que tener un bagaje detrás de datos analizados en los distintos tipos de SCADA que nos vamos a ir encontrando en las turbinas para ir determinando cuál es el problema real que se está teniendo en cada caso, ¿no? Por tanto, el problema que planteamos hoy es en base un poco a nuestra experiencia y con datos acumulados en una totalidad. En los últimos años hemos ido acumulando análisis en alrededor de unas 400, 500 turbinas, con el objetivo de intentar implementar sistemas que sean más sencillos a la hora de categorizar o saber qué tipo de problemas nos estamos encontrando en esas deficiencias de la turbina en sí, ¿no? En su rendimiento. Por tanto, el tema de hoy va basado en eso y cómo la importancia de tener estas bases en el orden de que nosotros pensamos que puede haber una serie de categorías fácilmente detectables si se hace un trabajo anterior, por lo que digamos que será implementar sistemas que nos puedan dar esa ayuda de más fácil detección de estos problemas, por lo que comenzaremos con un desarrollo o un análisis de esos problemas en sí para luego intentar categorizarlos por el tipo de problema que nos vamos a ir encontrando, y veremos durante la presentación que, bueno, nos vamos a fijar sobre todo en problemas relacionados con el tema de rendimiento, con problemas que nos puedan dar lo que es la conexión a la red de la turbina, y también muy interesante, pues problemas asociados con cargas estructurales que se están dando en ciertos componentes y que, bueno, está muy a la orden del día, ¿no? Desde un punto de vista de que necesitamos saber un poco cuál ha sido la operación de nuestro parque y determinar cuál es la vida útil remanente si es que la hay en nuestro parque, ¿no? Entonces va asociado un poco a eso. Por tanto, volviendo un poco al inicio, nuestro cliente o el operador del parque va a detectar un problema, va a preguntar al experto técnico, pero claro, cuando nosotros o el experto técnico intente profundizar un poco más en saber qué tipo de problemática tiene el cliente, bueno, pues contestaciones genéricas o típicas podrían ser del orden de: pues es que la producción es muy baja, o parece que la curva de potencia tiene algún problema, ¿no? Pero no se tienen herramientas para llegar a mucho más desde un inicio. Por tanto, vemos crítico un poco cuál es el estado actual de los estándares o de la literatura asociada o los manuales de funcionamiento de los propios SCADA desde un punto de vista de que no tenemos información suficiente para que sea utilizada desde un punto de vista más sistemático y ser utilizado para detectar esos problemas desde un punto de vista, como digo, pues, no se tienen descripciones de los típicos fallos o errores, ¿no? Es decir, cómo detectarlos, o no se tienen unas reglas muy definidas de cómo tratar los datos del SCADA para hacer esos análisis. Por tanto, queda un poco todo en base a la experiencia en este caso, el tercero técnico que vaya a realizarlo, ¿no? Por tanto, un poco la idea que queremos transmitir es que, teniendo unas bases un poco analíticas y desarrollando una serie de procedimientos, pues hay que intentar sistematizar un poco esa detección de anomalías y hacer una propia categorización, ¿vale? Entonces, bueno, simplemente yo quería comentar eso a modo introductorio. So it's time to change the language to English, and I would like to give the floor to my colleague Henry, who is in charge of this type of analysis in our department in Germany, and so is the proper person to explain technically and properly the process and the different anomalies. So please, Luca, if you can change the speaker to Henry, we can continue with him. Thanks a lot.
Muchas gracias, David. Thank you very much. Y muchas gracias por la introducción. Y lo siento para no hablar español, yo cambiar ahora también a inglés. Well, yeah, as David was mentioned before, we're facing a situation in the industry where we have no definition. The whole idea of this came out of a thesis work of one of my students. And he defines the issue by defining categories for the problems. Because when we speak about a problem, we have, as mentioned before, no clear connection to it. And we decided then, okay, we need to have kind of a sorting into it. And the first category he defines, no big surprise, it's energy. It's all about the money, meaning every issue we identify, it's turning around the mighty euro. The second category, it's not less important because it also can lead to an issue with money, but it's also related to where the issue is coming from. So, and we decided, okay, we need to have something which we can call now permit. Permit doesn't mean necessarily only the construction or operation permit. It's also connected to the permit by the grid operator, which is in some countries of the world, yeah, even above the law. We will even see like God. And the last category, which is also critical, but could be completely disconnected from the two first categories. It's about the lifetime or loads. That means issues we identify which have an impact on the lifetime of a single component or the whole turbine, or increase the loads. Of course, this can lead in the second phase then to violating the permit or to energy losses or additional costs. But we tried, in order to have here first definition, that we have a case sorted per category by its first error. So that is the theoretical background. In order to analyze the problems, this was not so easy, and we had to go two ways here. One way, which is quite typical when you do an analysis, you have a trigger, an anomaly, and variables. And if you don't know the output, you bring them together and see what happens. So, meaning you apply two variables, see if there's an anomaly, or if you bring in a trigger into the system, it causes an anomaly. And then you see a behavior. And this could be a potential error, which can be identified. But this is, when you think about SCADA analysis, it all not quite straightforward. Another way, which we brought into analysis, and this is also the way we try to establish here thinking into identifying errors is we know an error, and we are try to link the variables and the triggers to the issue. So an error, as was mentioned in the first example, my production is too low. This is the error. We already have the two variables we can see, and from these variables we can try to go after the trigger. Yeah, because sometimes it is important to know the trigger in order to understand the error. Let me show you on an example. In general, what I mean, well, we have plenty of different signals out of the SCADA. Here in this example, wind speed, pitch angle, wind direction, and many more. With those signals, we applied different combinations. Very common, everybody knows for sure, wind speed versus power. This brings us to the power curve, kind of a first standard. But this is actually not really defined. In literature, there is a power curve, but it is not really defined. And the classification of a standard in SCADA systems as a standard. It is more defined as a standard in terms of a contract, but not in terms of what you would expect an analysis standard. Another option is you just watch the time series themselves. I will come later on and show you how you can identify errors just by watching the time series. But what is common in all those ways is if you have defined a standard, you can go look after deviations in those standards or patterns, something which reoccurs. Can be, when you think of a power curve, all of a sudden dots which are not reaching the full power above nameplate speed. Well, and even though you have identified an anomaly, this was also next surprise when we were doing the analysis. It doesn't mean necessarily it's always an error. Just could be a turbine behavior which is unknown to us. So we had to make here the distinction between error and non-error. Does not mean that an event cannot be classified or put into a category. So even a non-error event could be something which is related to the yield, permit, or the lifetime. This was a big surprise when my student was presenting this to me, because a turbine is operating like normal, but we have an element in our operation which is causing an issue. So, next step, I want to go a little more detailed here. We see here a standard power curve. As I said, this could be a signal based on a figure based on two signals, power output and wind speed, common known in the industry. But if we define this as our base, this combination as our baseline, and say that upside from this standard power curve, everything else, a pattern, like here, where we see that the power curve is not reaching the maximum output, we would expect, even though the scatter plot here, much more dots in the higher wind speeds. We have identified an issue. The question is now, have we to classify this issue as an error or a non-error event? So to make clear to you how difficult it can be. An error could be simply that the turbine is switching off above a certain wind speed itself and reducing its output. But it could be also a non-error, just a regulation by a power controller which is not known to you, and the turbine is just reducing its power because the maximum power output at the grid connection point is exceeded. But in both cases, it would be a yield issue, because you base your model in the calculation of your power production, of course, on the full production. And if you're not aware of this issue, you have a loss in the money. Therefore, we said such an example would be a yield issue. Now, let me show you something which is also very simple, and not dependent on wind speed. We have here generator RPM and here the power. And if we just align those two signals, we get a curve. And every turbine has its specific curve. This is a very simple one, but we have seen some which go like this and up there. But especially in larger wind farms, if you have a larger number of turbines and see that they all have a common behavior and one is deviating, that indicates there is a malfunction. And this malfunction, in this example, could lead to a loss of power production, which leads to loss of money. Doesn't necessarily mean that your turbine is not operating well. And other example, we identified this on pitch angle versus power. Versus generator speed. So in this picture, you see the pitch is opening, the production is starting, the pitch is opening, keeping opening and going up. But we see here a lot of dots, this pattern. This is not normal. We were surprised because we saw this first, and then we compared another turbine of the same type with it and saw a complete different figure. And what we can see here is that the angle of the pitch was not fully opened, which was also, of course, loss in energy, because this picture angle is opening in wind speeds between cut-in and nameplate speed. So this is just identification. Keep in mind, it's just an identification of an error. I cannot tell you what is the loss now, but this is how to identify an error. Another thing where you need really close watch is degradation on power curves. So the first curve, which is up on top, was measured in the first year at my turbine. So most likely due to blade aging, we see how over the years the curves becoming worse and worse. So it could be also dirt on blade or damage. This is something which this part of the analysis cannot tell you, but I can tell you degradation of power curve means also degradation of my income. And then first example, which is also quite obviously visible, is a power curtailment, especially when you're not aware of it. What we here can see is the wind speed, which is above cut-in wind speed, and my turbine is usually operating. And here, this is at the generator RPM. We should see here at about 10 to 15 meters that the wind is at full speed on the generator, so we have not much deviation. And then we see this curve down here, which is now marked to make it more visible. The turbine is idling. Why it is idling, but it's not supposed to be? Well, one of the reasons could be reduced grid capacity. Of course, it could be also an error. As you can see, this is quite easy to identify with simple graphics potential errors or problems in the yield category. Let me go to permit category and speak about another option to identify errors. We have here two wind turbines with two wind roses. As we can see, obviously, they have an offset between the roses. And why is it an issue for the permit? The reason is that one of the turbines had a sector management. And if the turbine is performing its sector management in the wrong wind direction, and somebody is seeing it, it could mean that you get loss of your operation permit. But again, the identification that you're running into a problem is quite simple, just looking at the signals. So here another simple solution, and first time I'm introducing the opportunity to look into a time series. We have here again 2 turbines, and both turbines presenting the temperature signal. In this case, we have the issue that one turbine is giving you the wrong temperature. And I'm not sure how it's in Spain, but in Germany, we have a target temperature. And if the temperature is above the target temperature and the wind speed is below this target temperature, the turbine has to switch off in order not to harm the beds. But unfortunately, in this case, the temperature was wrong measured, and it was indicating that it's below the actual temperature, and the turbine was not switching off. Fortunately, it was identified before something happened to the beds, but in principle, this would be a violating of a permit and could run into an issue. This also very simple analysis step, just by comparing 2 power curves. What you need, of course, always is a baseline, and you need to be aware what's your baseline. The same is applicable then now for here another example. When we look into grid settings, we have here on the right side turbines getting the information that they have to set their reactive power. And as you can see, the set point and the actual reactive power are more or less always in the same range. No issue, no complaints with the grid operator. On the left side, we see this straight line here. And this straight line was found by comparing the set points against the actual values. And we can see that they are not met. And this could lead to the situation that the grid operator switches off your turbine because you're violating his law. And, the third, actually it's the first case for permitting is we have a limit. This red line represents the limit of maximum feed-in capacity from your turbine. And as you can see, this turbine was exceeding this limit. Yeah. In this specific case, there were actually 2 laws exceeded. One, which was the operating permit, which was only giving 3.3 megawatt output, and the other was by the grid operator, the requirement. Of course, you will ask that, but this all different cases here are simple, but as I said, we had no definition before, and the idea is to bring with simple methods the first definitions into failures. When we speak about this, we could bring much easier the communication between the operators and those who should support the operators in their work. Now let me show you some examples of the third group, lifetime extension. This time series shows the torque of an azimuth drive. An azimuth drive in a turbine usually is taking up to 25 kilonewtons. And what we see here is that we way above those 25 kilonewtons in a lot of cases. So the problem is that the lifetime of my single component is very much in danger because we have exceeded those limits. And the consequences could be now that not only the azimuth is breaking, maybe the turbine running into issue, but the main point is this is a lifetime example where my lifetime is reduced. Here we have other examples how to identify problems. Here in this case, I have a plot where we have the power output of a turbine versus the temperature in the stator. And as you can see, there is a very, very good visible curve in which for a certain power output, my generator should produce a certain temperature. And what we can see here, with a lot of operation points way above this temperature level. One risk is, of course, in a stator, as in the stator happened, is that the isolation can melt, we get a short circuit. Again, we have a lifetime reduction. Another example, which is also very easy to spot, is here we have in black defined our rotor RPM. This is how the turbine should behave. Rotor speed versus power output. And then we see in orange above another behavior. And especially when we come here around 1.5 megawatt, we exceed the design rotor speed. In this case, it's not so much, but this is already a problem because this exceeded rotor speed means also exceeded loads. In the worst case, it can come to a turbine breakdown. Oh. And this last example on lifetime I want to show you is how we can see just on a time series if my pitch is not doing well. As you can see here, we have from one turbine the three phases operating of a pitch. And we know by definition that pitch of a turbine is running between almost 0 degree to up to 90 degrees. So if we are slightly above or below, this is not an issue. But as you can see here over time, the turbine was going way above or way below this level. And this could be a problem. Depending on the construction of your turbines, it could be already caused a breakdown in one of your components in the turbine. And then I have here a special case, which is a complete deviation. And this is when my student presented this idea to me, something which I would call a little bit more advanced analysis. What we see here, we have here in light blue the CP curve of a turbine, which is given by the producer of the turbine. And what we see here in blue, dark blue, above the light blue curve, this is the measured CP curve. So what have we done? We have taken the values measured at the turbine and calculated them backward to see how the behavior is. And as we can see on this analysis, we are absolutely not within the design of the given curve. We have exceeded it. And even worse, we have exceeded the Bates limit. Those who are experienced with, of the CP curve, the maximum CP value we can reach is close to 0.6. So this curve is theoretically, physically not possible. Mathematically, yes, but physically not. And this indicates me that I have a problem most likely with my anemometer or with the values produced in the turbine. Something is not okay here. So I'm calling this a mixed case example because if my power curve is wrong, I have a wrong idea about the produced power output. But remember, the wind speed signal is also used to shut off and shut on turbines, for example, for a bad signal. That means if we are above a certain wind speed, we have to switch off the turbine or on. And therefore we could violate the permit. And in the last case, as most of the turbines still are cut off with the anemometer at the top, when it's reaching the cut out wind speed, the turbine could be cut off too late. So a turbine which should cut off at 25 meters is cutting off maybe at 26 meters, could reduce its lifetime expectation. So, let me give an outlook. So what we are ongoing now, we try of those cases I've just presented to you to develop more and to categorize them. Other steps in progress, I have another student, he's working right now on his thesis work to bring those examples we have seen from a qualitative assessment, means, okay, we have identified a problem, into quantitative form. That means, what does it cost to me? So my power curve is not producing 100%, only 89%. How much money do I lose? And what we also try to emphasize is a standard failure description. The idea then in the future is, and this is something which I'm thinking it's interesting, especially for those who are operating a wind farm, is that we're achieving, by applying those errors to SCADA signal, the understanding also with the turbine manufacturer that we have an issue which is violating my warranty. And if we have a standardized case and can confirm and by the standard that we have here exceeded in one way a limit, we would save the money to send an inspector confirming what we already know, and we can act much faster. And then for the far future, it would be also then maybe a use similar to a CMS system to use the SCADA data for a probabilistic failure identification. Means, okay, you see my turbine shows a tendency not to operate as expected. At a certain point, we have to act in order to avoid a loss of money or damage, or not to lose our permit. And then the last point, well, this is, I guess, partly implemented already in a lot of operational data by the turbine operators, is a real-time assessment. So you put your thresholds. Actually, you're doing kind of a SCADA analysis. You put a threshold for a certain temperature value, you put a threshold for a certain RPM. But this is only for a single value. And the idea is, if we have a standardized value setting, by combining and controlling 2, 3, maybe 4 values at once, we can identify a problem in a turbine on a much earlier way, and much cheaper than by applying expensive CMS system where only a few people can read the data and you need a lot of experience to understand them. So coming to the end, hopefully nobody is falling asleep. So we have, as I said, we have tried to use SCADA signals to identify problems, and understood that it's not so easy because we are lacking so far a real categorization and classification of the problem. And TÜV SÜD here suggests to start with 3 categories: the yield, the permit, and the lifetime category. Yeah, I'm at the end of my speech. I'm now open for your questions, or maybe you also want to add some questions to David.
Okay, thank you very much, Henry. Great presentation from both of you. Very interesting, with a lot of examples to illustrate how this analysis, what conclusions can be obtained. Thank you very much. Vamos a dar paso ahora al turno de preguntas por parte de los asistentes, por lo que os animamos a que realicéis vuestras preguntas a través de la herramienta que tenéis en la interfaz de GoToWebinar. A través de la parte de preguntas, ahí las podéis escribir, bien en español o en inglés, como prefiráis, y se las vamos planteando a nuestros ponentes. David, Henry, I am going now to to place you some questions, and I am going to send them to both of you, so feel free to answer any one of you as you prefer. I will try to make them in English. If not, David, you can also help me with some translation of some technical aspects, perhaps. But well, we have one first question, which has to do with the plots that you showed in your presentation, Henry. It's about these plots are made with average of 10 minutes or are made with other kind of information.
No, this is actually done with 10-minute values because that is what still is the standard in the SCADA world. Yeah. As I said, when we introduced the problem, we want to go not into high resolution data because they're usually not available to us as operator.
Mm-hmm.
Yes, in this case, normally we work with 10 minutes data, but in some cases, if you need to analyze very specific period, you also can use the trends data that are also available from the SCADA, but the standard way is with 10 minutes, right?
Mm-hmm. Okay, understood. Another question from Isabel Parrado from Tecnatom. You have shown several examples with two variables, models with two variables in your plots. Yeah. The question is if you also analyze other kind of models with three or more variables.
Well, I had one example. Just a second. We jump back. This is actually here. We have three variables here visible. What we see here is the blade angle, the wind speed, and the colored values are the production values. So this is how it could look like to work with three variables. So that you make visible, okay, I'm in this production range, these are my blade angles and wind speeds. But in principle, to combine three different signals gives us, increased complexities into the problem. But also, on the other hand, you can answer questions much faster. This is, of course, tried. As I said, we try, and when I was speaking about my outlook, we tried to bring more variables into those cases. We're not trying to stick to only one or two signal cases.
Mm-hmm. Okay, I understand also that this is an ongoing work that you are developing internally, so this is in continuous movement and improvement, no? I understand.
Yeah, right.
Okay, we have another question from Javier Calle. It is about how do you offer these services to your clients? Considering, well, the question is if it is done with historical data from the SCADAs from each wind turbine, or if it is an online monitoring system where you supervise all the information online, or both, perhaps. I imagine it is from you get the information, the data from historical data from the SCADA.
Yes, normally it's a specific request from the client, so we need to work with the historical data from the SCADA provided in this case by the client. But in other cases, if we have the role as the supervisor of the maintenance of the wind farm, maybe we can also to have the possibility to see the SCADA data in its case. But I mean, as a third-party technical advisory, normally we have the role only for the specific problem or for the specific moment of the wind farm and necessity of, by the client. I mean, change of a contract or some problems that have been detected in the wind farm. So normally we work with historical data from the SCADA. Yes.
So I mean, one of the issues, especially here in Germany, we face is that even this historical data are not so easy to get, especially for the operators. I don't know why, but we're struggling quite often to get all the necessary data we need when we do such an analysis. In order to watch and do an operational analysis, it would give us a much more complex role, as David was mentioning, and a lot of clients are in Germany not willing to give us, and maybe in Spain it's different, but say 99% of the cases are on historical data. So to tell the clients what could have happened or what we think what may happen.
Okay, here in Spain we also have a similar problem with historical data to be able to some developers to be able to share it or to obtain it. So I imagine it is similar to Germany. And related to this last question also, do you have any kind of requirement so that the data has to be structured in some kind of way to be able to perform this analysis, or any kind of SCADA is useful for this purpose?
And usually, of course, if possible, it would be good that the signals are sorted per turbine. But the big limitation we have is usually if we get data which come in a format from the turbine operator themselves, because they have their own data formats, they're usually not readable by the standard software. And another issue could be if we get data but no documentation to it, so we don't know what kind of signals we are watching here. These are the limitations, but in principle, if we know what signal we see and the data format is readable, we are not limited in order to work on the data. Just a matter of pre-work before we can start the analysis.
Okay, we have another question from Gunter Auer about the difficulties in defining the errors in these examples you were showing. It is possible, or how it is possible to set apart the errors from the non-errors in an automatic way? Is it possible to do so?
Yeah, well, this is actually what I said in my outlook, where we want to go. This question is directly related to the last point here, applying real-time assessment. Yeah, I mean, this is something you can do when you have the historical data, kind of smart filtering. Within our software, we can set certain filter methods in order to filter those data. But the automatic filtering, or let's say recognizing of those failures, it's actually indeed more interesting on real-time data. So for the analysis, of course, we try to automatize everything as much as possible. One reason is, of course, saving the money for the client. And the other reason is to be fast in our answers, because sometimes time is essential.
Okay, I understood. We have another question from Enrique Costa. He asks about what period of time do you use in your analysis, in your plots? You make a plot every month or every week or longer periods? What is the average period you consider to make these plots, or the lifetime of the wind turbine? I don't know.
The length, the time, of course, when I'm starting such analysis, of course, I try to look at the whole data set, because as we've seen on the time series, there are some obvious deviations visible. This already gives me first indication. But in principle, when I do a visual inspection, I'm trying to look in all those different steps. Of course, all those different steps showing deviations, and as I said, when we have set up a baseline, and we see deviation from those baseline, it makes it much easier to us to identify potential error. This is also what we try in an automated way to train the system and saying, okay, this is our baseline, and here we have exceeded the baseline.
Okay, so the problem must be how to build this baseline, no? With what data. Then to compare it with the pattern.
Well, this is what I have emphasized. We need to have a standard. We need to agree on a standard. And if this standard is accepted and we see deviations from the standard, it's much easier if you go into the discussion with the turbine supplier or with a grid operator, depending on your issue.
Okay. We have another question from Ernesto Blanco. He asks do you combine the data analysis with physical inspections to complete the troubleshooting or to confirm the results?
Yes, of course. Usually what we try to do is the analysis front up, and especially for end of warranty inspections, to give our inspectors clear indications for the components or parts where they should look into, or confirm if you find an error. As I said before, that the failure in the SCADA analysis is usually not accepted by the turbine operators. So we have to bring, so to say, the smoking gun.
Okay, but we also do that service.
Here also we can comment another example combining analysis and inspections are related with lifetime extension, because it's needed before a data analysis of the wind results, then the loads suffer by the structural components, but also, of course, an inspection in the wind farm in order to check the conclusions by the analysis. Yeah.
Okay, Sergio Fernandez points out a similar question about this, and well, in the case that you use other departments or you get support from other departments, as for example mechanical or blades, to make these on-site inspections or these on-site works, can you give some kind of examples of these experiences? For example, how can you get a first idea that there is a problem or an underperformance from the analysis of the data, but then you have to confirm it, and well, the question is if you have some examples using this methodology.
Yes, maybe as mentioned before, no, the survey for lifetime extension is a clear example to combine a physical work and also the analysis, because the objective is to analyze the operation of the wind farm during the whole life and to see what type of wind resource has been receiving by the turbines, and then to do a simulations for the loads in the structural components in the turbine and take some conclusions in order to know what is the remaining life in its part. But also is needed, of course, a physical inspection in the wind farm in order to have clear if the theoretically cases are true or not, or what is the real state of the components. Yes, maybe it's a clear example. I don't know if Henry can explain another one.
Yeah, no, well, I mean, I've shown, let me see if I can find it quickly. This slide here on the jump shortly to this one. Yeah. What you can see here, this was actually done a SCADA analysis before we did a warranty inspection, and we saw those exceedance here. And based on this findings, we said, okay, please take a deep look into the azimuth drives. And this analysis has confirmed that on this specific turbine, the Azimuth drives had huge problems. We found that the Azimuth drives, when we inspect them, were close to an end of their lifetime, which was unpleasant for our customer, because they were supposed to run 20 years and they looked after 5 years like they were already 25 years in the field. This was a very clear example. Another example, let me show you another example, was where is this? I'm looking for the pitch. That is this picture with pitch angles. Wait. Okay, no, I don't have it. Cannot find it, because I had a picture with the pitch angles, where the pitch angle was exceeding the. Here, but sorry, directly here. So, and what we saw here is that the pitch angle were over, and this were electrical pitches, and they in the turbines they have actually a mechanical stop introduced, that the pitch, the blade is not going over the stop, but it was a run over. We found a run over the traces directly in the pitch system. So we told our inspectors, look, we have here seen some cases, please have a look. And when they came to the site and looked, and they could find on those specific turbines those run over markings. And we at the SCADA signals, and therefore we could clearly prove, look, Mr. Turbine Producer, we have here an issue with the pitch system. So these were quite obvious cases where we could directly link our findings. But of course, I assume if we understand this deeper and coming further, we have in the future the option to give the inspectors much more ideas and evidences in hand that they identify the errors directly on spot.
Okay, yes, very clear examples. Thank you both for them. I have one last question. It has to do with the categories that you have shown that you use to categorize or to classify the problems that you can find. Why do you use these 3 categories, or are you looking also to develop new categories, or are they demanded by your clients?
Regarding the categories, these were at the first stage the 3 obvious one, because when we were going through all the requests we had were either something related to money, something with permits, or something with the loads. Theoretically, you could imagine other categories, but so far we haven't faced them. If we see out of the request there is the need to develop a fourth category, we for sure will try to introduce it, but so far we haven't seen a third one. Our student had looked in about 50 projects and a lot of requests when he was doing his work, and he nailed it down to this 3 different categories. He couldn't find any specific category outside. Even those 3 categories are already maybe a little bit too much, because as I was emphasizing, that they are sometimes linked to each other. But if we have an indication that for a fourth category, then of course we would introduce it and try to define it and to link cases to this category.
Yes, as you point out, these 3 categories are so global that they cover most of possible problems. Okay, well, we have arrived to 5 o'clock, which was the time scheduled. I think we are going to leave it here. It has been really interesting, your presentations and your answers to the questions. Thank you very much to both of you. Thank you, Henry. Muchas gracias, David. Y muchas gracias a todos los asistentes por haber estado conectados con nosotros. Y por mi parte, nada más. Piluca, te cedo la palabra. Y muchas gracias a todos. Y un saludo, y en especial a David y a Henry por dedicarnos vuestro tiempo y vuestra sabiduría.
A vosotros. Muchas gracias.
Muchas gracias
Bueno,
por invitar.
Gracias a los tres, Henry, David y Tomás. Ha sido una cita muy interesante. Habéis hecho posible que entendamos un tema tan complicado como es el que llevabais hoy y que sepamos más del mantenimiento de los aerogeneradores con los datos SCADA. Muchísimas gracias a los tres. Hemos conseguido además que los asistentes se queden hasta el final y eso es la mejor señal de que lo que habéis transmitido era interesante. Antes de despedirnos, me gustaría anunciar las próximas citas para todos vosotros que organizamos en la Asociación Empresarial Eólica. La primera es el día 13 de mayo. Es una jornada sobre autoconsumo y la eólica. Es un tema muy particular que lo vamos a organizar en colaboración con Reoltec, con la plataforma tecnológica de energía eólica con Reoltec, y será el 13 de mayo de 10 a 12. También os podéis inscribir de forma gratuita, por supuesto. Y el siguiente webinar será el día 20 de mayo, lo hacemos en colaboración con la empresa Leasoft y será sobre las previsiones de precios y la visión de futuros en el sector de la energía. Estáis todos invitados. En nuestra página web podéis tener acceso a todos los eventos que vamos organizando a lo largo de este mes y el mes de junio. El Congreso Eólico será el día 16 y 17 de junio, también ya podéis inscribiros. Y nada, recordaros que tenéis esa pequeña encuesta esperando para que nos ayudéis a mejorar y que mañana a primera hora recibiréis el correo electrónico con el link a la presentación y a la grabación de este encuentro. Muchísimas gracias a todos, a los ponentes, al moderador y sobre todo a los asistentes, que es para los que hacemos estos eventos. Gracias y que tengáis todos muy buena tarde. Adiós.
Un saludo.
Adiós, buenas tardes.